Welcome to This Explainer. Today, we're taking the highly technical brain of your computer, the CPU, and breaking it down using a setting we're all pretty familiar with, a busy restaurant kitchen. If you've ever wondered how your machine handles rendering massive files, or just, typing up a document without skipping a single beat, you are in the exact right place. We're going to decode this vital piece of hardware, not by staring at silicon and microscopic circuits, but by stepping right into the fast-paced kitchen of a master digital chef.
So, here's the menu for today's explainer. First, we'll meet the digital chef, then spend a second in the kitchen, explore the anatomy of a CPU, figure out what drives CPU performance, and finally, see your CPU in action. Let's jump right in. Section 1. Meet the digital chef.
The Central Processing Unit, or CPU. It's universally known as the brain of the computer, right? It reads instructions, processes data, performs calculations, and basically controls the entire system. But to truly visualize how it handles this massive, non-stop workload so seamlessly, let's look at it not as a microchip, but as the head chef of a world-class, high-speed restaurant.
Let's go ahead and map out our kitchen. The CPU? That's our chef. The software or program you're running is the recipe. Your data equals the ingredients. Your long-term storage, like your SSD or hard drive, well, that's the refrigerator. But when it's time to cook, you obviously don't leave your stuff in the fridge. You move it to the fast-access kitchen counter, which represents your RAM. So the chef reads the recipe, grabs ingredients from the counter, cooks, and serves. It's literally that simple.
All right, moving on to Section 2, a second in the kitchen. Every single tiny action your computer takes relies on a relentless, incredibly fast four-step process happening millions of times a second. First, receive. That's taking the customer's order. Second, understand. Reading the recipe. Third, perform, doing the actual chopping, mixing, or cooking. And fourth, send, plating the food up and delivering the final result. Let's apply this to a super common daily task, opening a web browser. The chef receives the Chrome recipe. It pulls ingredients from the SSD fridge right onto the RAM kitchen counter. And hey, if you use Chrome, you know it takes up a lot of counter space. It processes everything instantly and serves the web page straight to your screen. A totally flawless, multi-step workflow executed in the absolute blink of an eye.
Which brings us to Section 3, Anatomy of a CPU. Let's step completely inside this kitchen.
First up is the control unit, or CU. Think of this as the kitchen's lead expediter. It directs the flow of data and tells all the other components exactly what to do. It's basically the voice shouting out the orders, making absolutely sure every part of the CPU is operating in perfect harmony.
Now, if the control unit is giving the orders, the arithmetic logic unit, or ALU, is the heavy-duty chopping block. This is the roaring stove where the actual mathematical heavy lifting and logical comparisons happen. Whenever the computer needs to know if 5 plus 3 is 8, or check if one number is greater than another, it goes straight to the ALU.
So, where do you hold ingredients in the exact middle of cooking? Registers. These are ultra-fast, microscopic storage locations right inside the CPU. If RAM is the kitchen counter, registers are the chef's very own two hands, holding the exact ingredients being actively chopped at that precise microsecond. It is literally the absolute fastest storage available. Next, we have cache memory. Think of cache as the pockets on the chef's apron. It stores handfuls of frequently used ingredients, maybe like a pinch of salt, so the chef doesn't even have to walk over to the kitchen counter to grab them. It keeps all that vital data as close to the action as physically possible.
Okay, Section 4. What drives CPU performance? Essentially, how do we upgrade this kitchen to serve more customers?
The first major metric is clock speed, measured in gigahertz. This is basically the pure physical speed of our chef. A higher gigahertz number means faster hands, allowing the CPU to chop ingredients and cycle through instructions at a blistering pace. More cycles per second simply means more recipes finished.
But, one fast chef can only do so much during a crazy dinner rush. Modern computers solve this by adding more cores, like dual-core, quad-core, or octa-core setups. Adding a core is essentially hiring extra chefs to work independently in the exact same kitchen. So in this case, having too many cooks in the kitchen is actually the secret to incredible multitasking. And to make each of those individual chefs even more efficient, we introduce threads. Threads allow a CPU core to handle multiple streams of work way more efficiently. They act almost as separate hands for a single core, allowing them to juggle multiple tasks, like, say, actively stirring a pot of soup while simultaneously checking the oven. It ensures no chef is ever just standing around waiting.
Finally, Section 5, your CPU in action. Let's pull back from the microscopic details and look at the actual meals being served.
Every single application you use relies entirely on this workflow. Whether your chef is coordinating complex rendering logic with your graphics card for a heavy AAA game, responding instantly to your keystrokes in Microsoft Word, or swiftly decoding a 4K video file, every single thing you do relies on this invisible, lightning-fast culinary process.
So the next time an app opens instantly, take a second to appreciate the billions of tiny operations happening right now in your device's kitchen. It is an absolute marvel of engineering. Think about the tasks you're running right now. Are you pushing your digital chef to earn its Michelin star, or just asking a master culinary artist to boil water? Thanks for joining me for this explainer, and keep exploring the incredible systems that power our digital world.